Now we are all set.
And now is everyone happy? I will not do that for the third time, my friends. So I go right away to here. So there has been a quest. People have tried to develop in situ operando methods or bring spectrometers to the real reactor. But what you also have seen is that in the 1960s, microelectronic devices have been developed, which led to the chip industry, which brought actually a lot of surface science methods. Surface science methods have been embraced by the catalysis community as well. And it has led to surface science methods, which has been, for example, used for having single crystal facets studied in great detail. But when that appeared, this kind of, I would say, dichotomy, where you had the world where you had infrared, NMR, EPR, and all these methods, which developed and tried to bring them, you had at the same time a development in this model catalyst, ultra-high vacuum techniques. This is, I think, an apparent dichotomy at this moment. You see these two worlds actually merging more and more. And that is what is, I think, what I show here with this arrow, that you see that on one hand, surface science methods will try to push towards more realistic ambient reaction condition. Think about X-ray photoelectron spectroscopy, XPS, where you now have commercial instruments for ambient XPS. On the other hand, what you see is that people also, and I will show you later on some examples, where you really try to see if surface science methods can also be pushed into operando. This was somehow my introduction, and last week I actually noted that some people were twittering, I don't know who, but they actually took this picture. I did not do that. So, but here I saw here this thing, and that seemingly this picture took a lot of attention, and there was some explanation. And then at some point, someone was saying that instead of having this special animal, we could also have this Swiss Army knife. Now, I was told by Christophe Copéret that we are used as Belgian or people from the Netherlands, that red one, but seemingly it is this one, which is the real Swiss Army knife, if I understood. So I hope I have, but I think the point is clear. What you have is you want to have an all-in-one device, but you also have to be realistic with your Swiss knife, that if the challenge is big, then maybe your scissor or whatever will be not that effective. So I think we should be also realistic. So what I want to say with this is, if we want to develop methodologies and we want to have it all in one, you also have to accept its limitations and its capabilities and its limitations. And before I'm really starting then with the point I want to make for this second lecture is, these were somehow the take-home messages from the last lecture. So one is realistic experimental setups as well as catalyst materials have to be taken, which mimics the catalytic process as best as possible. A second is that we want to acquire useful characterization data, and that means that you have to put a lot of emphasis on in situ and operando cell design and construction. I will come to that in a minute. And the acquisition of complementary information will be essential, because it's not that when you want to be Hercule Poirot, you will have to need a lot of different tools, which allows you actually to solve the murder mystery game. And last but not least, measuring is perturbing. So it means that stability of your system under reaction conditions will be essential, and you can have beam damage via X-rays, by lasers, by electrons, but not only can you have beam damage. I think last lecture I also showed that temperature gradients and temperature effects are also have to be checked. So as for today, I would like to give you a sneak preview. That is, that today I would like to show you at the end of my presentation today, which will be the second half of the lecture. We will have a break in between. I want to talk about what would it take if we want to make a movie of a catalyst particle. And by doing this, I will introduce you a lot of methodologies which allows you to do this. So today I will talk about X-ray microscopy, single molecule fluorescence microscopy, electron microscopy, combinations of techniques, and so on. So this will be your menu for today. And I would like to come back to my question 4 in my tutorial last week. And I had some response, actually. I hope for more response, but some of you at least responded. So I have material, and it is almost about EPR. So you have a very, I would say, active EPR community here. And so that is the reason why the showcase I will discuss today will be about EPR. I will talk about Operando electron microscopy. You will see that I discuss a lot on Operando infrared. Then I will try to show you some bridging of the materials in Operando gap, and then a molecular movie and some, what's next in Operando spectroscopy and analysis. So before answering or coming back to one of the questions which were posed by you students, I want to come back to this, I think, almost essential slide which I showed you last week. If we want to design a proper in situ Operando cell, then we have to think about the catalyst material and also about the cell. So I think important is there a cell activity by itself? Cells are made out of metals and whatever, so you have always to measure just your background conversion. I cannot say it enough because you can really have sometimes activity, especially when you go up to 500 degrees and whatever, because then you have that. I also advocated for cell volume control, or better, reduce the cell volume so you don't have back channeling and so on. And of course, the spectroscopic window has to be proper, because if you have, for example, a silicon nitride window that is good for measuring carbon, but assume you're measuring nitrogen, then it's not working. And the other way around, if you think you have a silicon carbide window and you're measuring carbon, that also leads to a lot of background. Today, I would like to focus on one technique, and you will see it 3 times appearing, and it is infrared. And I want to focus on the catalyst 4. So here you see Ana Hernandez Jimenez, a former PhD student in my group, and this is her setup. I agree, it's a bit messy, but there you see the heart, which is an infrared machine. And then you see a gas panel on the left. And on the bottom left, you see a mass spec. So you can do Operando infrared. This is transmission. Transmission means you make a pellet by putting on a powder pressure. Now, for those who have done that themselves, they know that that is, for certain materials, far from trivial to make a self-sustainable thin wafer, which can withstand later on the heating and whatever. For certain zeolites, it's notoriously difficult. I can tell it with my own hands. As a postdoc, I actually had 10 times, and then 2 times you have success. 1 out of 5 is not, and I'll say an exception, depending how skilled you are. So maybe I was not that skilled. This is a transmission cell, and actually you see here an optical fiber in the middle pointing towards, because we actually hooked in also an optical fiber UV vis. And this has to be contrasted with this spraying mantis. It is based on diffuse reflectance infrared. Now you say, what the heck? Well, I can tell you it matters. Because for transmission, it's more easy to quantify. Lambert-Beer is in principle, if you do it well, applicable. The optical path length can be assessed. You can make a self-supporting wafer with a press. I already mentioned that it is not for all materials that easy. If it fails, then you can add a kind of binder material, provided that binder material is not influencing the thing. But then we say when you have a press, you press. So are you not structurally modifying your sample? Question mark. And most important, you have a wafer. Do you still have transport through that wafer? Is there nothing affecting your catalysis? It's easily compatible with other methods like UV-vis and Raman. Actually, you can just hook in everything almost what is optically feasible with an optical fiber or whatever. Now with diffuse reflectance, actually here I show you, you have an instant beam and then you have specular reflection and diffuse reflectance. That's the bottom right for those who are following it online. The optical path length is not easily accessible. So you can use an internal standard, I come to that, to get it possible to quantify. You have powders, fine particles. So in principle, you can use your solid matter as it is. That's the advantage. And if you're making sure that the gas has to go through the bed via this, here this on the left, actually you have a cup where your powder is brought in and you make sure that the gas goes through it. Then in principle, that powder which you measure via your diffuse reflectance component should be possible. However, the whole dome around it has gas. So still that is also an issue. I think that one of the persons who knows a lot is Frédéric Meunier. And here I show you a recent paper where he actually discussed the pitfalls and benefits of in situ and operando diffuse reflectance. And here you see some of his things he is discussing, amongst others, quantitative spectroscopy. I wanted to select two things out of that. The first is on the left top, for those who are following it online, I just showed you a paper where it is NO exposed to a palladium titania catalyst. And you see it before and after NO exposure. After is with the red, black is the before. And then you see bands appearing on the left top. But you can also mix this with barium sulfate. And then you can also bring it into this SO vibration. And when you do that, you can see that you can plot a calibration line. And then you're ready to do, provided that this barium sulfate can be added and it's not intervening with catalysis. That is, of course, with an internal standard with the risk that you are doing something what is not needed or not wanted. Another alternative is to make use of the internal support bands. The right example is one where you have the zeolite lattice vibration or better the overtones, and where isooctane has been absorbed on a zeolite system 5. You see on the left, the 3000, 2800 region in red is the isooctane's CH stretching vibration. And then you can correlate it. And in the bottom part, you see again that you come with a calibration line. So this allows you to follow quantitatively the reaction. Later on, I will show you a third example of infrared, which is attenuated total reflection, ATR infrared. But back to my question, which I asked you last time, design a combined operando cell for your own work. And I was happy actually to receive this one, as well as this one. And they actually both are about EPR. So Alan, and I hope I pronounced it right, Puente Urbina Arturo, I don't know if I pronounce it well, but Alan, I will email I will come up with a proposal for your, but it was also about EPR. In this case, he wanted to know, can we detect gas phase species above the catalyst bed? And here I have another one, which is actually from the Jeschke group here at ETH Zurich. Jörg Fischer, Michael Agrochev, Simon Schlapansky, if I pronounce it right. And they have been proposing for their EPR on the left, a system where they can do Raman UV vis together with EPR, expand, and where you can do online activity measurements. So the fortunate thing is that I did during my PhD already EPR. So this comes from a class I'm giving at Utrecht University on the right. It's actually a picture or an image of an X-band EPR, and in practice, such an instrument looks like this. I think the crux of EPR, or the problem with EPR, is that you don't have a lot of space. You have a cavity with your sample, and that's depending on the cavity actually, but with X-band it's still large, and then you go to Q-band, it's smaller, and everything has to be confined in a very limited space. And that has to be put between these magnets. I've been looking up the Jeschke group's papers, and I just found this paper. Sorry if I did not took the right one, but here you can see the design which has been taken by this group, where you see the cavity. There is actually there where the microwaves are brought and then comes in resonance with the system when a field is applied to this paramagnetic species. On the top part, you see a sample tube. On the bottom part, a hot gas is injected, so you can actually heat up this sample in the middle. On the right, you see how it is looking like. And if I understood, it's actually a homemade system or a homemade modified cavity for doing this. And a nice example, in my opinion, is one from together with Perez Ramirez group, and Javier Perez Ramirez is actually doing a lot of work on chlorination type reactions. So here you see the oxychlorination over a system, two systems actually, chrome phosphate and europium oxide chloride. And on the left, you see the cavity again, with there the sample in the middle, the green, and then you see the gas injection on the top. And what is the most important is then when you see scheme B and C, there you can note that you have actually, when you have helium versus this propane oxychlorination, which is indicated by POC, then you can see that the signals actually change, and that has been measured by the europium 2+ fold, or the chromium 2+ fold, which is actually nothing else than the chromium 3+ reacting away. That is actually what is here assumed, and then you can quantify it and link it. But back to the question from the group. So they were saying, Bert, this is our proposal. Is this something what makes sense? And that brings me to one of the pioneers in this field of catalysis for having EPR in the operando mode, and then later on combine it with different techniques. And I think that full credits has to go to Angelika Brückner in Rostock in Germany. And I know that in this country you speak this language. So I actually thought I select a German perspective review article where she, and I must say also, I felt it was, I think, the latest, I'm not 100% sure it's the latest review, but one of the latest reviews from her group actually in 2014, where she discusses. And in this paper, as well in the papers which are indicated in the reference, you can notice actually that they have been, that this group has already bringing in this UV vis and Raman. And I think, okay, then case closed. So I answered your question, but I thought that's too simple because I want to give you more a perspective. And this is most probably the most advanced Operando EPR experiment, where next to UV vis, they also do ATR infrared, and they also do X-ray absorption spectroscopy. And they literally have their magnet at the synchrotron. So they bring, as I mentioned before, the spectrometer to the beamline, and they used actually the rock beamline of the Soleil synchrotron in Paris. And you can find this article here, and it looks like this. So here you see on the top left, the schematic with the EPR cavity with the X-rays in, X-rays out. And then on top of it, you see this Kapton tube, and there you have this dosing or whatever. And then actually you see that they have been doing a lot. Then they have the ATR infrared, UV vis, probe head, and so on. So I thought this was a nice example of this Swiss army knife. So where you have a lot of tools together to try to tackle the issue. Now, remember last week I showed you that technique combining helps you also to evaluate if there is something happening or not. So I think it's very nice that you can see on top here the UV vis with copper. On the right, you see the xanes with copper. You see here the change in the EPR signal, and also you see the change with the copper signal. So you can really bring and see a lot of things together. So this as a kind of answer on this question on combining methodologies. Today, I want to make a lot of emphasis, as I mentioned, on infrared. I already discussed transmission, diffuse reflectance, ATR will come. But before that, I want to discuss, which is a technique which is also emerging and is getting very popular as well, which is Operando electron microscopy. And I will show you an example, which is CO2 methanation from own work, actually, which we, due to a collaboration with Sarah Bals of the University of Antwerp in Belgium. A pioneer in the field of one of the pioneers, it's always difficult to say if there's one pioneer, it's Crozier, Peter Crozier, and I found this review paper from 2016. You can note, actually, it's called in these days still environmental TEM because of the environmental cells, environmental transmission electron microscopy. And it goes hand in hand with high pressure STM. And the goal is, can you really go to the atomic scale? Last week, I already showed you this kind of cells. These cells on the right, they have transparent areas where electrons can go through, and you can bring in a gas in between two plates, and then what you have is a wire. This wire is a platinum wire, and a platinum wire can heat, and you can have flowing gases. Although Crozier is a pioneer in this area, I think the most spectacular images which we have been seeing and has been brought forward were by the Danish groups, Topse and also Hansen and Helveg, Stig Helveg, which is now a professor at DTU in Denmark. And this work is, for example, an example where you can really see that catalysts change their shape, react when a gas is added at reaction temperature. And in the green, you see the facets of a copper particle on a zinc oxide. And then you can clearly see the left is in hydrogen, the middle is hydrogen with water, and the right is with hydrogen and CO. And clearly the system responds, showing the relevance of in situ operando. Another hallmark paper, which is also from the same groups, and now you see Helveg as a first author. He's now, as I told already, an independent scientist, a professor at DTU. Here you see in situ transmission electron microscopy of a nickel catalyst where a carbon tube is actually growing at the end, and that you can elucidate how that is happening. and you see snapshots from A to H. Since then, because these papers were from, as you can see, the 2000s, since then, actually, a lot have happened. Here I put here two recent review papers from Dong Tzu and from Schlegel, Roldan Kuena. And they provide you a lot of background on cells, what you have, and so on. Currently, there are 3, it's actually commercialized. You can buy instruments with a proper cell. There are, and I hope, I mean, I'm not having any shares in this company, so just to make that clear. And I'm also not myself the electron microscopy expert, but I spoke today actually with Sarah Balz, and she told me actually that are the 3 major companies which are out, Dense Solution, Protochips, and Hummingbird. And at these websites, you can find movies, and their movies show their in situ cells, Operando cells. The point I want to make as with the showcase, before I go to the CO2 methanation, and I want to actually focus that one of the intricate things in catalysis is what is going on at the interface between a particle and its support. What is happening there? There's a paper from 2022, this year. It's actually a Chinese group with a cooperation with people also from other countries. And here you see a copper zinc oxide catalyst, and you have the top image, just hydrogen. Then you can actually have the reaction condition, the steam reforming of the methanol, which is, for example, this middle panel, and then the bottom panel. And what you see is that that you start to make an overlayer of zinc oxide in this copper. People are actually arguing, is a support or a promoter? What is happening? Do we add it, and does it make an interface? And here you can note that because of this electron microscopy, you can do also elemental analysis and do that right. The example I want to discuss is something from our own work. And there we work, as I mentioned already, together with a group in Antwerp. The system is something where some of you are also working on. It's CO2 hydrogenation. And you can make methanol, you can make methane or whatever. And the system which we have been studying for some time is nickel-based catalysis, where nickel are metal nanoparticles which are capable of converting what is called a Sabatier reaction, making this methane. And it's a really multi-scale. This is the reactor, 5 centimeters is the extrudates. Then you have this porous metal nanoparticle, and here you see on the bottom right a nanoparticle of about 5 nanometers. So the setup is indeed from one of these companies. You see this cell holder on the left bottom where you have this chip which is added and where the catalyst particle is in. Then you have a front part of this electron microscope, which is the gas supply system. It's also shown on the right image. And you have the online GCMS, which allows you actually to analyze what is going on. So the first is, can you reduce a catalyst in hydrogen? And what do you then see? So this is, for example, 400 degrees C, where you have titania as support. And remember, titania is a reducible support, so it's not innocent towards the nickel metal nanoparticles. And the fun thing is that when you have this particle with all its facets, and you can try to identify the 100, the 111, the 110 facet, that at some of them seemingly there is titania, a shell. And to prove that, I show you here, and let's first start with the top image in the middle, which is an electron microscopy image. And then you have the blue arrow on the left, and there you just see no shell and the nickel 100. On the right, in red, actually you see that at some point you see a titanium oxide contribution. Now you can say, how do you know that? Then we have the bottom image where you see these squares of blue, red, and black. And we have actually yield spectra on the right, and you can indeed identify them. When you go again to the bottom right from the red arrow and you follow it, then again you see this titanium oxide. The question is, this is hydrogen reduction. We call that strong metal support interaction. Sorry. Can you now do that operando? Because this was just in situ. On the right, you see the online GCMS, and although it's not much, you measure methane. So it works. And on the left, you can note actually that the particle, partially the titanium will creep off the particle, and also the particle becomes more rounded. With 600, it is more on it still. Good. So this was an example of Operando electron microscopy. I'm quite sure that many things will follow out of this technology, and more groups actually are trying. And I also understand here that ETH, there is a group very active in there. I promised you that I want to continue on the infrared. So far, we discussed gas, solid. There is also something else. That is gas, liquid. A very recent review, actually, by Laila Negadar, and also people from the UK. She actually has a review on this solid-liquid interface. ATR infrared is a technique which allows you to do this. And what is important is actually you have to have a special crystal, and then actually you have an evanescent wave where somehow you go out, and then near the surface of this crystal, you can pick up signals from the infrared. We have been using this methodology, and I will show you actually a kind of summary of 2 articles where we have been following the depolymerization of lignin. Lignin, a compound which is giving strength to biomass and plants. Our setup, and it's the second most common of abundant biopolymer, as they state. The setup is shown here on the right, the picture on the left is set up. And this setup allows you actually to go up to high temperature, high pressure. And typically you can reach something like a few tens of bars even, and let's say a few hundreds of degrees C. It's a typical PAR reactor. So like 200 degrees, 20 bar is a reaction conditions. We have been using it for cutting kraft lignin, or lignin in general. And this is the wood in the middle, and then you have different lignins. Kraft is that what is coming out of the pulp industry, the paper mill industry. It's a waste product currently burned because of energy recuperation, but it will be useful if you can make some aromatics or other compounds of it. Years ago already, we started more than 10 years ago to work on lignin. And one of the reactions which has been actually invented by, invented is always a strong word, but by Jubesic's group in Madison, Wisconsin in the US, is aqueous phase reforming of glycerol or other compounds, which is shown here with platinum aluminum. And one of the ideas was, can you now not do that also for lignin? And that was our work actually. We thought, can we just cut it out? Because you see this polyalcohol glycerol unit, and can you then make aromatic compounds? Now, that looks on paper simple, but what is it in reality? So on the left, you see another reactor which we had actually made, especially made for us. It's not made by us ourselves, but it has a window. So you see on the left bottom, you see that optical window, So this reaction allows you to put, for example, UV-Vis or Raman as techniques. I will not discuss that, but you can now make snapshots of the process from going from the left, 0 minutes, to the right, where you have this reddish solution and some solid. So it works, but this color does not tell you a lot about what is happening in the chemistry. So now I will almost go through the thesis, where I want to show you how we have been developing. Khaled Khalili is a PhD student. The methodology of ATR infrared to monitor lignin depolymerization. So what do you as the first? Back to this calibration line before. The first is, what is my operational window? When do I see something? So here on the left, you see the spectrum, solvent, 1 weight percent lignin, 5 weight percent. I hope you agree that the green spectrum is a bit the tricky one. And when you have 5 weight percent, you start to see something. Agreed? So then you can measure further. So you say, okay, from 5 weight percent, I add more and more lignin. I hope you see that spectra of lignin are very complex. It may not wonder, they contain a lot of groups, including aromatics. So if we have this, we can make a calibration line based on these, for example, 1100 and 1200 bands. And it works. So you have now a calibration line. Okay. But we don't have yet catalysis. It's just we add lignin and we measure and we make a calibration line. Then we want to go for catalysis. But the first thing, is my reactor ready to do that? So what we found out is that you had to purge the system for a long period with nitrogen to get actually all the CO2 and water vapor contribution in that cell gone. I hope you see some rotational band and also some CO2 band there in the left top. And here you actually on the bottom right, you see how long it takes. It takes actually, let's say, almost 300 minutes to get it ready. If you don't do it, you have this kind of contribution, the spectrum will just be complicated further. Last but not least, you heat up the thing. And when you heat up the thing and you have water around, what then? To remember is, the solvent you increase from 23 to 225 and have a look, the spectrum actually comes more stronger OH bound. Actually, you have less hydrogen bonding, hence a shift. It's important to subtract at the correct temperature your baseline. If you measure your baseline at room temperature, subtract the room temperature baseline of the solvent, good luck, but that is not the truth. So here I show you then on the bottom, the top left, you see the solvent and the lignin measured at 225 and 30 bar, you see? So then you start to see something reasonable. Okay. Yeah, I mean, now I'm now really going almost through the spectrum by spectrum. It sounds maybe, but it's almost like it is a tutorial. So I thought, let's do it. Good. So then you can have a net Kraft lignin spectrum. You just subtract still. You have a bit of wiggles there in that circle. But nevertheless, you actually from the spectra and the spectral changes, you can actually monitor the temperature. The spectra have in it the temperature. That brings me to something, because it means you can make a partially square model that from the spectra you can check if indeed the temperature which you thought it was is the case. Okay, this is still boring because you say, okay, I have now everything done. But now starts to be the interesting. So we thought, can you use the Operando ATR infrared spectra to predict the molecular weight of the lignin, actually the depolymerized thing? Can you determine that? And we took spectra. So we took samples and measured actually with size exclusion chromatography what the sample is all about. So we have ATR infrared and size exclusion chromatography, and they should somehow, they should match somehow. Can we then do that? So here, the spectra, as measured, nothing special. Then we did solvent correction. Now we start to see very nice spectra, at least on the right end of the thing. Then, and now I have to forgive me, we did some chemometrical appliance to it to get it back, adjust for additives, baseline, scattering effects, and so on. And then you can apply principal component analysis, statistical routine to say, what is the variance in the system? And what it is actually, you see here, principal component number. The first one is clear, the second one is also clear, then it's the third and the fourth, and around the fourth to the fifth, everything is explained. So we have spectra, and I will not explain them now in detail, but you can have aromatics, the OCO mode of a G unit, things like that. An alkyl aryl ether, typical for lignin. And this is a plot I want to explain because you have principal component 1 and 2, which actually dominates the spectrum. And you see all these lines going to certain vibrations. And now we are able and have in red, for those who follow online, you see 1, 2, 3, 4, 5. So you see this 1, 2, 3, 4, 5. It makes a curve and then goes to 19. This. And they all point to their major features. And what you have is, first, you have actually the typical lignin, and then later on, actually, you see that somehow you make this guaiacol type species. You have offline analysis by size exclusion chromatography. You can overlay them, that's on the top left, drop in molecular weight and polydispersity. And then you have more aliphatic. So you again have this 1 to 10, and then 10, 11, 12, up to 19. And these things allow you now to make a model. In the model, here you see predicted molecular weight, measured molecular weight, and it's almost a straight line. So from the spectra and its features, although it's very difficult to identify all the features, but there are fingerprint features. They allow you to do molecular weight and polydispersity analysis. I will do this and then we take a break. One of the things I felt that, and I know I saw Naresh actually, Naresh Kumar. One of the things is, I mentioned at some point in the beginning also, and also last week, we have actually what they call the materials and operando gap. But actually these two worlds are more and more just drifting to each other and will merge at some point. And if you push on one side and push on the other, at some point there will be overlap. So this is a slide I showed you last week. And I said, single crystal is a lot what has been done in, for example, vacuum techniques, ultra-high vacuum techniques, and so on, STM. Supported nanoparticles, I already showed you an example. And when you go to what I call this industrial catalyst, and then I was actually a bit provocative and said, well, then you cannot do anything with this TIP, AFM, atomic force microscopy approach. What is there out? There are several methods, actually, there's a whole revolution going on. And I want to refer to this review paper, which I think is a very excellent one, which is a cover of Chemical Society Reviews, actually very recent, with actually also an author from this university, Zenobi. But I also it's fair to refer to some of these others. The whole point is, you have a tip, and the tip scans over the surface and you can have topographic information. You can actually have height differences. But on top of it, you can actually bring in a laser and try to obtain spectroscopic information. In the cover on the left, you see AFM infrared, atomic force microscopy. When you have an infrared laser, you can do then infrared. And TERS, tip-enhanced Raman, is when you come with a visible laser. AFM Raman, you could also have written down. I want to explain you first this tip-enhanced Raman spectroscopy. Tip-enhanced Raman spectroscopy actually exploits a very important, is this needle or this tip on the left, which you see has a roughened appearance, which is very important because at roughened surfaces, you actually will have plasmon effects. Actually, there you can, and as shown on the right image, you can also even calculate it. So what is this sample? Is you have this tip, you have an excitation laser, and then you can measure. We have worked some years ago, we worked together with a group of Deckert, Germany. This is, I think, one of the first examples of a reaction where we have been following a photocatalytic reaction, where on a gold nanoplate in the middle, you put a thiol group, for example, para-nitrothiophene, and this nitro group can be reduced, amine, and then actually come together, and then you make what is called DMAP. It's actually a dimercapto azobenzene molecule. And it's clear that this nitro group is very Raman active, and this double bond nitrogen is very Raman active too. So you can follow that. So here I show you, and I hope the movie will work. Here you see the starting molecule. We actually then excite it with another laser, and then the reaction will actually go on. This dimerization reaction, and then you see right away a lot of things changing. And you see that this DMAP also pops up. And on the right, you see actually the whole process. The red laser is to measure, the green laser is to the reaction, the red laser is to measure again. You can really do that. So this is one of these first examples, and you would say, okay, react, analyze, it's piece of cake. And I think that someone here in the back of the audience, Naresh Kumar, the first author on this review of protocol article in Nature, actually will right away have to admit that this is far from trivial. And one of the things which is far from trivial is, for example, the stability of the tip. We actually have encountered a lot of issues with the stability because you have to make sure that this enhancement is always prevailed. But that is not the case. And here I show you on the top, the bottom part, I see on the right part of the slide, I show the tip in air, in water, and here I show you the TERS contrast, this is red line, as function of time. And one of the ways to get it protect is to try to make a layer around it to stabilize it. But then you, of course, have an enhancement effect as well. I will not talk about TERS further. I want to talk about this AFM infrared. And this is a machine which we have actually at Utrecht. And this machine allows you to do AFM and infrared in the nanoscale. And here you see the setup. And we have been using it also for in situ, not yet operando. I would say it's a bit on the edge. You see here on the bottom left, a sample cell. And we actually can bring vacuum and gas in it. So it's 2 watts. And we have been studying, for example, HCUST1 and ZIF8, which are responding to water. Actually, we have been studying the water or water vapor stability. But that's not the reason why I selected it. Because I wanted to show that you can follow a polymerization process of olefins at a kind of a Ziegler type catalyst. So can you take snapshots? And for this, I want to come back to this model system. You have AFM, so it means you cannot study everything. So remember this gold film for the thirst. But what we did was we have been making a surface and a pattern, which is on the top right. In the top right, you can actually load on it lanthanum oxide chloride islands. You can also do it actually with magnesium oxide. And then we took lanthanum oxide chloride because it's rather stable. Magnesium chloride not. Once you have, and then for those who are in olefin polymerization, they know that you can then start to put, for example, titanium on it. And when you do that, you have actually a dome, kind of small island, and you can start to do this surface science method. And here I show you that we indeed are able to make polyethylene fibers. I think on the left, you see this kind of spaghettis in black. And here on the right, you see actually a FIB-SEM, focused ion beam, scanning electron microscopy image. So a side view, where you see this polyethylene, the lanthanum oxide. And that is, now we are ready to do this AFM infrared. And here I show you, left the topography, right the PIFM. So here you see the hydrocarbon, the polyethylene growing. So we have been following it as function of time, which is actually pristine to 60 minutes. And you see these spaghettis. And here I show you on the right, from 1 minute, 2 minutes, 5 minutes, 10 minutes, 20 minutes, 60 minutes, you see growth of these fibers. And a nice thing is that you can do that really space resolved, because here topological information is the top, the spectroscopic information is the bottom. And we have now focused on one wavelength, and you really can see that this topological information translates in spectroscopic information. And that's nice because now you can really identify spaghetti lane by spaghetti lane, which is a polyethylene fiber. And to show that it is really true, here I show you this spectroscopic information again, 0 minute, 1 minute, 2 minutes, 5 minutes, 10 minutes, 20 minutes, 60 minutes, all fine. But I want to focus on the 5 minutes, and there, for those who follow online, they see 3 triangles in different colors. And they are just taken outside the fiber. You agree? 1 is on the fiber and 2 outside. So here you see the spectrum. In the spectrum where you really see this flat background, there you see these 2 bands which are typical for this plastic formation. And that we have been analyzing again with some chemometrics and whatever all. And then you have different components, amorphous crystalline, and that you can follow as time. And here you see on the right, the crystallinity increase. Actually, it goes rather fast. And of course, there's some error on it, and you can argue if in the beginning, 1-2 minutes, if there's, as you can see, a substantial noise level, but still, I think it's already neat that you can follow with PIFM at a nanoscale fibers growth. And that is where I want to have now a break. 10 minutes? 10 minutes. And then we end with the last point I want to discuss. That I want to end this tutorial by showing one example where we have been working for years on. And I don't know how many I will show due to time reasons, but I want to show you that it takes perseverance and dedication to try to get a level of understanding in a system. And I would like to be this person here where I'm making a movie of a catalyst particle. So can we go to a molecular movie of a real life catalyst? And the real life catalyst, which we have been studying, I could also have shown another system which I discussed while I was giving the other lecture, the more general lecture here at ETH. which would be cobalt, titanium, Fischer-Tropsch. There we also have been working for years on. The other one, which we have been working a lot, is on fluid catalytic cracking. It's a realized system, it's complex, and it's used in oil refiners nowadays. And here you see, for example, one in Rotterdam or near Rotterdam in the Netherlands. Now you can say, okay, oil, crude oil, over. We don't use it anymore. I think that some recent developments have shown that we are, although we want to move away from fossil resources, that it is not that trivial. But the nice quote, nice thing is that this catalyst has also other opportunities, because you can cut in pieces crude oil. There are also other hydrocarbon chains, and one of these hydrocarbon chains, now you understand, which I show you, is plastic, is also a hydrocarbon chain. So this hydrocarbon chain on the right is also something what you can maybe cut in pieces and then regenerate, recycle. And that idea is not that silly, because in crude oil, you find reducible metals, which come from the fossilization process of biomass millions of years ago, iron, nickel, vanadium. And now you have in plastic another metal, which is actually the titania, the zirconia, the chromium from the metallocene, Ziegler, Ziegler-Natta, and Phillips catalyst. Now this catalyst looks not simple. This is a scanning electron microscopy image. And every day in a huge installation on the left, fresh catalyst is added in a continuous process where the crude oil of the feedstock is mixed. And that cycles between this pipe, which is the riser, and goes back to the regenerator, which is on the left. The catalyst itself is a mixture and consists of binder material and zeolite. And the binder material is alumina, silica, clay, together with zeolites. It is used for crude oil, but more and more people are also trying to see if alternative feedstocks can be mixed, and maybe we can somehow at some point actually see if these refineries can be built towards other feedstock. And to show that, we actually did polypropylene cracking with these catalysts, and you can make aromatics, for example, out of them. Now, one of the things we forget is FCC catalysts, fluid catalytic cracking catalysts, are made for cracking crude oil, which is a bulky molecule, but plastic itself is also a very bulky molecule. So it's not that trivial to do. But that to justify, and now I want to go towards molecular movement. So here you see this man, and he is making the movie. And what I will do is I will show you a movie which we made years ago. And now you see here the process of fluid catalytic cracking. You see here the reactor, two reactors, and actually they go into the riser. And now we zoom in on the catalyst particle. We know already these spheres, I just showed, and here are these spheres. So here you see the sphere. Wow, this is the catalyst. And now we jump onto a crude oil molecule, and that is what the crude oil molecule will see. It will see a gallery, and then it will see crystals. These crystals are the zeolites, and what you see on the ceiling and whatever is all alumina clay. And here you see a crude oil molecule going into the system. Chaka, cut, chaka, cut. And here you have a gasoline molecule, for example. On top of the riser, and you see on the top right image, the white image there you see. We have to remove all our molecules. We just showed 3, but there are many. And now we go to the regenerator. The catalyst actually is blackish, brownish, and you have to burn off the coke. And then you see these measles in red on the catalyst particle. Actually, they penetrate into the ball, in the sphere. And what you have is actually the metal poisons. And what do? They kill the zeolite by destroying the illumination of the zeolite. And after a while, you don't have acid side. So this is the movie. And now I want to show that it's true or not. Okay, that's the challenge. I told you we need a lot of methods. And here you see the whole list. I hope you're convinced this you cannot do with one postdoc, one PhD. This is an effort of years. And it's literally, I show you at the end some pictures, and then you see, actually I was this morning, or I told actually Christophe, I was so surprised if you can put all the pictures together that you think, okay, this was some effort. I want to ask you two questions, or solve two questions. Can we make street maps of a catalyst particle? What is the influence of the metal poisons? Okay. Can we make street maps of the catalyst particle? We actually started our adventure at SLAC in Stanford, where we have been using two beamlines for Dixon and X-ray fluorescence. We have been developing actually initially not for this, but for Fischer-Tropsch. Now you see that sometimes things go a bit further. We have been using this transmission X-ray microscopy setup where we built an Operando X-ray nanotomography setup, which you can see here in the middle, which is the cell. And on the right, you see the very tiny capillary where you put the catalyst particle in. If you do it successful and you rotate, then you can get this movie. This is not the movie I showed you, the kind of Hollywood type movie, but this is real life SLAC X-ray tomography. The reddish orange is actually iron, greenish is nickel, and you can actually see 3D through this particle. This particle itself is micrometer in size, and you measure nanometer down pixels. Yep. Okay, this is nice. But can you now get something out? So this is the particle. It's about, you see, 50 micrometer in size. Optical density, iron and nickel. And now we start to analyze it. So where are the measles? You remember that I told you the measles? That I said the measles with the metals. Where are they? So here we actually have the particle. We make subsections, and actually you have these kind of volumes. And in these volumes, you can actually see where the iron is and where the nickel is. So the iron is in reddish. And actually here the nickel. Do you now already note that here, so this is somewhere here. Now I show you the next one. So now I move to the outer part of the catalyst particle. So next one. And now you see that what you have is a shell of metal poisons. And when you go deeper and deeper, you have less. Actually, the metals are Pac-Man. They eat into the particle. Now I have later on to show that then also the zeolite is damaged. That comes later. So what you can do is you can now analyze the pore volume. You can actually determine where it is. And the nice thing is now you can start, because I promised you that I want to show you that you can make street maps. So now I want to go like Google Earth. Can we now do catalyst particle Google catalyst particle? I don't know. I just invented it. So here is the particle. And we fly through this pore network of a single catalyst particle. So now I just invite you. These are real data. Eh? Now and we make a street map of the catalyst particle, and you can follow it. So now we dive into this three-dimensional space built up from all the material. And you have nodes, these balls, and then you can be at a traffic light, and you can go left, right, and you can go up and down, because here you can go in 3 dimensions. See? You can say, okay, great, fine. What did I learn? Yeah, I know that the metals are somewhere located. So we worked together with a certain industry, where we had access to a real life plant, and we actually had industrial catalysts taken out. what you can do then is you can separate them on H. And when you have them, you have here particle H. And what is the reason why you can do that? Because you can separate them based on density. Because the more metal, the more dense, so you can separate them. So we had actually 4 particles. These 4 particles I call fresh, low metal, medium metal, high metal loading. Yeah, that explains the abbreviation. And now here you see the iron concentration on the left and distance from the particle surface. So the left is the particle surface, a lot of iron, the peak. Then you go to the right and you see less. And what is that doing? It actually changes the porosity. So there where you have metal, you block. Good. So we say it somehow as a rotting of an apple. So the fresh is the fresh apple. And when the Pac-Man eats the metal poison, and you actually get this rotting, and you see to this bottom right, you see nicely this orange-brown layer, which actually is the iron. And in the middle, you have a fresh particle. Actually, the idea could be then, if that's technically possible, that you peel off this layer and then you have again a freshly exposed. But that is overly complex. Now, so far, we used XANES and we use X-ray absorption near edge spectroscopy. But the problem with this is that you have to measure these edges. One of the techniques you can use for identifying elements is X-ray fluorescence. X-ray fluorescence you can also do at a synchrotron. And we took a particle, we measured the top X-ray, transmission X-ray microscopy, and then we also measured the same particle with X-ray fluorescence. Now the fun thing is, and that's also a long story, we actually had at some point almost like a suitcase with catalyst particles. And we traveled with these particles and we had several to analyze. So it sounds a bit funny, but it's really like you do the science, because you want to make sure that you measure the particles and with the same technique. Because we did not only this, we also, for example, did fluorescence microscopy and things like that. Okay, what we did is we identified all the elements, iron, nickel, calcium, vanadium, many of them. And then we say, can we now make it as a resistor network? So if I want to travel through the pores and I'm meeting a lot of metals, then I'm not easy to go further. So that is this resistor. And then you can have, when you go from A to B, you see you determine in these voxels the elements, and then you actually go further and see. And that leads to this move. This brings all the results together of where the elements are in 3D with X-ray fluorescence. And now we combine, so this is 3D. Spatial resolution is not that great yet, I have to admit. You will see that it improves over time in the spatial resolution. Now you have them all together. And now we say, okay, this is the porosity network in white and black. And now we see this reconstructed particle. We take an element. And this element, we dive into the thing that you have already done. Oop, here we are. And then we go through the pores. I like this. Because it shows that you now can really go into it. But also you can note actually, because now it's still free pores. And now start to add elements to it. Here, now we add all these poisons. And then diffusion or transport is getting more difficult. This was 2016. And now you think, okay, were you the first? Well, you find out when you write a review that sometimes you thought you were first, but that is not the case. So here is actually a paper from 1991, where people have been trying it, actually this catalyst system as well. However, have a look, in these days, this is the setup, the resolution was 10 micrometer and 10 micrometer. I think it's fair to say that we have seen an enormous progress. And here I see 1991, 2014, 2016, and I hope that this image really shows that it's like when, I'm a bit older, if you think about the TV, the screens of the TV, then they were in, when I was a kid, they were black and white even, and then you saw it getting better and better. And if you now see a screen of a TV, I mean, it's almost like you have the cinema at your home now. So it's amazing. So that also holds for synchrotrons, pushing, pushing, pushing. And this is something what we did together with people, beamline scientists at beamline P10. There they have a technique where I will not dwell too much on, but it allows now to measure with another approach, holotomography and fluorescence. So far, I talked about the metals. You agree? I think I convinced you about the metals, but about the carbon, you did not see yet. So this carbon deposit, you not see. So what we did is we actually have, again, and that's the good thing, we had access to an oil refinery. We had the capability to take the catalyst, which was on top of it, before it went to the regenerator. That's a good sample. So that's what we did. So here you see the sample with carbon deposit, the uncalcined and the calcined. You can do a subtraction thing, and then you can get this. Now I hope that hopefully should turn. I don't know what happens. So that's a pity if that does not work. Yeah. No, on my screen it works. But now you have to believe me, it's more fantastic than before. What you can do is you can measure the carbon deposits, a lot of parameters you can measure, and I hope still that this works. So this works, yes, great. And now what you can do is you can know where the carbon is. So this is a volume which we take out. And here actually, I show you that when you go through it, I hope it will work now, that you can note actually in 3D where carbon deposits is. Now what we did is we measured it before and after calcination. So we know where the carbon is. And then actually here, this is where the carbon is in black. See, you know now where the carbon is. You know where the carbon is, you know where the metals are, and you actually can even get flowing through it, because that is what I want to show in the next, I think. I hope the movies work. Sorry, it does not work. Here, so what we take this volume, and we now say, actually, can you now, this is the roadmap, and now actually you can just have molecules in a computer flowing through that thing here. These are where the channels where molecules can go through the thing. And now we open up the thing and then you see the different molecules. So this is a computer taking the model from the X-ray tomography, I have to say. And then you just say flow where you can flow. Now, you can not only measure the carbon, you can also measure there where the, you can not only measure the carbon, you also can measure actually where the iron in the carbon is. And I would like to focus on the right image. The orange is the iron, the yellow is a carbon layer. You see? So that is how far you can go. Now you can say, okay, a movie, but I did not see molecules moving. So what we did is we have been using single molecule spectroscopy, and we used not an oil molecule, but a molecule on the top left, at the bottom left. This molecule is with these all aromatic rings. You can have a laser, and when it put a laser on it, it will emit, and you can have that in this FCC particle. So that here I show you here. You see, this is what I want to follow. Can we do this? Of course, otherwise I would not tell it. So here you see single molecules moving around in this particle. And then you have many tracks, 4,000 about. And these tracks, you can follow the molecules in this particle. You can actually even know where they are. You can even put a diffusion coefficient on them. The fun thing is, what we found fun was many are immobile, just sitting there, or they are escaping our spatial resolution because maybe they move a bit around. That is also possible because you have not the right spatial resolution. Or, and that is what we also think is, they are adsorbed actually to the wall or to the material, and therefore not observable. So I hope I've convinced you that we can make this bottom left, we can visualize the highways. And also I hope I've been able to visualize the metal deposits, these mesols. Yeah. So next question. Can we visualize the internal structure of an FCC particle? And can we see the zeolites? And can we see that the zeolites dealuminate? And what the metal poisons are doing? So we did fluorescence microscopy. I already showed you that before. And with the fluorescence microscopy, you can actually identify the zeolites. Why? The zeolite catalyzes an polymerization reaction, gives rise to this green dots. And the green dot on the right is actually an image of thiophene polymerization, but styrene, they all do the same. So we can visualize it. Now you can say, okay, I want to do it single molecule. So on the right, you see a movie, single molecule. It's another reaction, furfuryl alcohol polymerization done by the zeolite. And everywhere you see this dot, this flash, there the reaction goes on. So it's zeolite catalyzed. If that's the case, then we should be able to, and here the top left image is this yellowish orange actually are the zeolite domains. So we can identify the zeolite domains. Now you say, okay, are we sure? So then we go further. We introduced actually this Naresh word, Naresh Kumar. We took tip enhanced, not Raman or infrared. No, we did tip enhanced fluorescence. So we measured fluorescence at the tip. So we made a very tiny slice out of the FCC. We did the same, and actually this domain there in the circle, that's a zeolite domain, which you can identify. And you notice actually it's a 0.5 micrometer in size. And that's about the size. So, okay, you can do further. So far, you did not show an electron microscopy image of a zeolite. True. I only showed some fluorescence and highways. Okay. So we thought, this is an old electron microscope, and we build in single fluorescence microscopy. So we do exactly as I showed you before, but now we do it with electron microscopy and fluorescence. The whole trick is beam damage makes that you first have to do the fluorescence and then the electron microscopy. If you do first the electron microscopy, no fluorescence anymore because you just have damaged everything. So here I show you on the left flashes, single fluorescence microscopy on an FCC part. On the right, I show you electron microscopy. And that is now nice because what you can do is you can now start to overlay it. So the TEM on the left, in the middle, fluorescence, on the right, we combine them. And what do you learn from it? What you learn is that there are areas where the material and the material, the crystals, and the fluorescence overlap, and at some points, places not. Where does it not overlap? Here I show you a zeolite Y image. By the way, you see 100 nanometer. Remember what Naresh showed was something of 500 micrometer. It's not that far from the reality. See? But for those who see well, they see actually that there are holes in this cheese. You see the zeolite crystal, and there are channels. Yeah. So it means actually you damage the zeolite. And we have been able to correlate fluorescence and the damage of the zeolite. Actually, you go from undamaged zeolite on the top, very nice crystals, mesoporous, macroporous, up to fragments and amorphous material. You say, okay, if that's the case, then we have to have dealumination. True. Zeolite has to be dealuminated. We went to Canadian light source and we did aluminium X-ray microscopy. And when you do aluminium X-ray microscopy, and you can also measure other elements like iron, lanthanum, but we were interested in the aluminium. And aluminium allows you, in the bottom part, to distinguish between tetrahedral, octahedral, and mixtures. Zeolites should contain tetrahedral aluminium. So when we see more and more going to the right, we see dealumination. And that you can do space result. So on the top, on the left, you see the images. The X-ray spectra are on the left. And on the middle, where you see red and blue, you see actually the degree tetrahedral versus octahedral. And the fresh, you see that you have still also octahedral. But here with the ECAT, which is actually a damaged one, you see that sometimes more than half the aluminium is gone. Okay, if that's the case, then we should see it in the X-ray diffraction, no? And that is also what we did. We did X-ray diffraction, X-ray fluorescence, and X-ray absorption spectroscopy. And what is the message? Here, this is a rather busy slide. But here you see X-ray diffraction patterns in the middle with the 2 theta. And you see in the top one, which is actually the one who contains a lot of nickel, you see this shift in peak compared to the ECA2, which is actually not that damaged. You see that the X-ray diffraction peak shifts. And the nice thing is you can measure that locally, micro X-ray thing. So you can measure locally what is going on. And what is happening is you actually have nickel or metals interacting with the material and damaging it. So that means that I've been able to show these flashes of activity, not cutting a real crude oil molecule, but I hope I've shown you that I can show you the reverse, actually, the formation of a molecule at an acid site. I also showed you porosity and damage of the zeolite. So what is the conclusion? So I showed you that movie. I'm not saying the movie is the truth, the Hollywood movie, but at least you can see that you can really try and get this insight. This is a huge effort, and I felt that I should show all these people here in a slide. So thanks to them. And also a lot of funding. Which brings me to my concluding remarks. And I have this slide. What's next? What's next in Operando analysis? I think here's an arrow. Nobody knows where, well, this plane, not know where it is flying to. At least it was for me flying home. So that was a good thing. But we discussed before, time, faster and slower. Faster, you want to push the limit and go to like with free electron laser or whatever, you can want to push it too fast and things. On the other hand, you also want to go slower because you want to study the real life period of a catalyst, as I mentioned last week. You want to measure days, hours, months, even years if possible. Space, I showed you, small, but also large. And also, I think, combining methods. And this multi-scale real-life system I showed you in the previous thing. But that is, I think, what you can all write down on a small piece of paper. I think every one of us will recognize the lab, and I think that everyone has these kind of labs from the lab, but we also notice that we are undergoing a revolution, both in informatics but also in robotics. And I must say, I like very much, I mean, there's a paper from 2020, actually. It's a group in the UK, and it has this kind of robot. So this robot walks around in the lab and makes a lot of catalyst and whatever. This is photocatalyst, actually. You can think about, what about this robot in an Operando lab and doing a lot of things? I think we will see more and more where this kind of robotics or informatics will come in and will change the way we actually conduct. What would it be if you would be at a synchrotron and you had this robot and that you would be doing it from home? From Utrecht University, I'm actually steering this robot at the Swiss Light Source in Villingen, where that robot is actually doing all the change of the switching this and whatever. I'm not saying it will happen, but it's not unlikely that these things could at some point. And another thing is, and that I also showed you, is we see miniaturization. And many of us have been having these tests for COVID and these small nanoparticles which detected the COVID. You can also think about, can we not sense the health of a catalyst? Can we not sense the health of a reactor? And based on these sensors, which are based on Operando approaches, you actually are monitoring the health and intervene as a doctor, a medical doctor, but now a catalyst doctor. You actually are changing the conditions to get the catalyst again rejuvenated, again healthy. You give a bit more vitamins, a bit more promoter here and there, and then it starts again to work well. And that would mean that you have a different way of looking to catalysts, because you maybe keep the catalyst in the reactor, but you're more carefully knowing what you can do to get the thing again running for a while. And all of that will be spurred by a lot of money. And there is a lot of money in this refinery of the future. We sometimes as chemists complain about life science having a lot of money. That's true. But I think we also have to be fair that we have an enormous challenge in front of us where we want to make our society more sustainable, more circular. And that means that we have to develop new catalysts, and that Operando spectroscopy can help, like theory and other things, artificial networking. A lot of these things will help as tools to find the new cutters and pasters of molecules to make our fuels, materials, coatings, whatever. And my last slide is that you have a ball, which I would say is silver, and you want to go to gold. And that means you want to use your brains, your tools, your techniques, and what you will have to do is to explore an n-dimensional space in a wise manner. And this n-dimensional space in a wise manner means that you want to use your resources, spectroscopy, theory, or whatever, so that they guide us from there to there. We have already good catalysts. Can we have better catalysts which actually work for doing process of the future? So that is what is called sometimes this material genome. Can we speed up our search for better catalysts? Thank you for giving me the opportunity to present these two tutorials, but thanks should go to these people because they did it. Thank you for staying here until 7, a little bit later than I thought. Sorry. Again, for this very nice tour. So he is in ETH till the end of June. His office is D109. He answers to email, especially if it's about science. So administrative not. So feel free to connect with him, and be happy to answer your questions in the coming few months, and even later if you want, because Utrecht is not so far. Okay, so thank you very much, Bert, again for a nice tour. Thank you.